Hi, my name is Ivan Ramirez. I am a master's student at Georgia Tech in the Intro to Cyber Physical System Security class. And today we will be talking about CommanderSong, a systematic approach for practical adversarial voice recognition. Before we get started, I did want to give credit to the folks who actually put this research together. It was a collaboration among many different universities, including the Chinese Academy of Science, Florida Institute of Technology, the University of Illinois, as well as the Indiana University of Bloomington. This paper was presented at the USENIX Security Symposium, August 15th to the 27th, 2018 in Baltimore. So I wanted to just, quickly reference them and the work that they did here. So let's quickly go over the outline of this presentation. We'll first spend a few minutes giving a quick introduction as to what it was that the research paper was actually trying to accomplish and explain how the team at a high level went about actually testing and demonstrating their findings. Then we'll go a little bit into a deep dive of the background of the state of the technology that was used in order to perform the test, but also what is currently being used out there that could be a potential vulnerability, such as different ASR systems that are widely used. We'll then talk about existing forms of attacks that exist on these platforms and a little bit of the research that has been done in this field or lack of research. We'll then talk a little bit about the motivation and the actual experiment effectiveness and results. And we'll finally summarize everything in a quick conclusion. To start off, and at a very simple high overview level, the concept behind this research paper is quite simple. With the mass adoption of technologies such as the Amazon Alexa or the Google Home and any other speech recognition software that is found in apps and so on, is there the ability or is there a vulnerability to an over-the-air attack towards these devices? The paper doesn't go into detail as to what these threats could potentially mean, but as more and more people adopt the smart home or integrate all their different assets, let's call them, into these ecosystems, you could easily see how this could be a really big deal. Again, the paper doesn't go deep into it, but one of the example commands that they have is open the door or pay, ask my bank to pay this person, right? One can easily extrapolate that to be very dangerous, especially if you're familiar with the mass adoption of integrated smart home cameras, microphones, linking to bank accounts, linking to photo repositories, and so on. The threat is definitely there. Now, as part of this experiment, in order to define the success criteria, the team, as part of this research and experiment, decided that there was 3 main goals that they wanted to achieve. The first was to be able to effectively have a real system recognize a command, right? If they can get a real system to recognize a command, okay, that's check number 1. Check number 2, this command should be stealthy and unnoticeable to ordinary users. So we should be able to find a way to hide it. So this won't just be a speaker telling an Amazon Alexa, hey, do this, but it should be it should be unnoticeable, right? And then the third criteria would be capable of delivering this remotely, right? Is there any way that this attack could be mass propagated? And that these are the 3 main topics that we'll dive into during this presentation, talking about how each one of these were achieved. It's also worth mentioning that the team used an open source ASR system called Kaldi. It's available in GitHub, and they basically use this in order to generate a lot of their inputs for the CommanderSong, as we'll see in the next few slides. So now that we have a high level of understanding to what the research paper is actually about, let's take a step back and dive a little deeper into the background on the state of the technology. So we mentioned earlier that the adoption of devices and software that utilizes speech recognition has been increasing in the last couple of years. And things like the Amazon Alexa, the Google Assistant, Apple Siri, Microsoft Cortana have become more and more commonplace. The research paper also mentions a couple of Chinese companies because a lot of the research team was based out of there. So the experiment actually tested against iFlyTech speech recognition in order to see if their attacks actually worked against it. And then they also tested against that one and against a different one to see if there was any effects between ASR systems. We mentioned earlier that the team chose to go with the Kaldi open source toolkit in order to generate these attack commands, and we'll talk a little bit more about how that was done in the next few slides. But when we're talking about speech recognition, there's two main components that come into play. The first is the feature extraction, where the individual noises that make up a specific word are separated, if you will, so that this set of noises was one particular word, this other set of noises was another particular word, and then that raw data broken down in that way is then sent to the decoding in order to, and at that point we would use machine learning to actually map those specific words that have been broken down into the likelihood that it would mean a specific word. So common acoustic features extraction algorithms include the MEL frequency, Kepstral, the coefficients, MFCC, the linear predicate coefficient, as well as the perceptual linear predictive PLP. Obviously, a lot of time and research was involved in the development of each of these, but that wasn't the main focus of this paper. Now, in the extraction side, that's when we really get into the machine learning side of things, like how do we map those features to actual words and the likelihood that might happen and slight variations on how people pronounce different things, or even like the tone of the voice of the person actually speaking and so on. So it makes sense that here we would use machine learning. So the three most common methods are the hidden Markov models, the Gaussian mixture models, and then most popular, most widely used recently are the deep neural networks with hidden Markov model integrated into it. Now let's spend a few minutes talking about existing attacks against image and speech recognition systems. Now, the research paper goes into two known avenues for people to attack these systems. The first is a very simple brute force method where we actually, where an attacker would actually get access to the model or to the data set building that model and would manipulate the model or the data set in order to change the results, right? So instead of having a specific word mean something, they would map those specific phrases to mean something else. And that is one way that attackers currently could tap into the system and attack it. The other way that was far more interesting and inspiration of the icon that I put in this presentation was something called the dolphin attack, which actually proposes a completely inaudible voice attack that exploits vulnerabilities in the actual microphones of the devices that are listening, right? Human ears don't have the ability to hear noises beyond certain wavelengths, but microphones do. So by sending commands via these frequencies, we're able to actually send attacks to microphones without humans ever being able to detect it. Fortunately, this was brought to the attention of a lot of manufacturers, and the research paper actually quotes how the iPhone 6 has actually implemented different methods by which they block those signals to ensure that these commands or vulnerabilities addressed. The paper then goes into talking about the motivation for the research paper, as well as highlighting some of the philosophies that they will follow through the experiment. So the paper quotes a lot of research being done in attacks against image recognition classification systems, but none of them really address the text-to-speech. In particular, given the improved intelligence of deep neural nets that have made tremendous advancements in the last couple of years in the realm of speech recognition. So that was one of the main motivators for actually pursuing this research. Now, the team chose, as part of the way to satisfy the three criteria that we had spoken about earlier, one of the criteria was that this attack should be unnoticeable to humans. And given that the dolphin attack that we discussed earlier had already been implemented and fixes have already been established around that to not allow microphones to have that type of vulnerability, the thought came that hiding the command within popular songs would be another way that the user could be unaware that their Alexas or Google Homes are picking up these attacks unconsciously. Now, to give a little bit of restriction and constraints, the songs in questions would not contain the exact wording of the command, nor would it contain, 80% of the words. So if it was open the door, we wouldn't have the door as part of the lyrics, because that would be way too close to what the command would actually be. Now, as part of trying to inject a command into an existing song, an algorithm would be developed that would try to find the place within the song where the least amount of changes would have to be made to the actual audio coming through in order to still achieve a command that was recognizable by the microphone input in the Google Home or in the Alexa device. Now that we've gone over the motivation and philosophy for this experiment, let's dive a little deeper into some of the details as to how the experiment actually took place. How is it that we accomplished, or that the team accomplished, what they were looking for? And just talking about high level some of the findings that they were able to uncover. So in the experiment, the team generated over 200 CommanderSongs that contained different commands and attacked the Caldi open source system that was serving as the base ASR technology. And they were able to do this with 100% success rate in a WTA attack and 96% success rate in a WAA attack. The difference between a WTA and a WAA attack is WTA is literally giving the raw format to Caldi as a file, and then Caldi analyzes the actual file and then outputs a result. WAA is actually done over the air, so that was literally having a speaker playing the sound and having a microphone running Caldi actually recognizing the speech in real time. Now, to understand the human perception of the attack, the team also conducted a study using mechanical torque, Amazon's mechanical torque. Mechanical torque is like a marketplace, if you will, for mass testing or mass surveying of folks, so you can determine like the number of participants, the tasks that they have to do, the age ranges, gender that you're looking for, and so on. And Amazon's Mechanical Turk will actually go ahead and help you source these participants. Over these surveys, we'll share charts in the next few slides. We actually compared different types of speakers. We played different songs. We showed different commands, and they essentially asked the folks taking the survey whether they found the song strange, whether they could tell if there was a command injected in the song, and if so, what the command was. We'll review the results in the next slides. The team also identified 2 ways to actually defend against CommanderSongs. Those 2 methods were audio turbulence, in the sense of adding digital noise to the songs in order to disturb them enough where the command was not recognizable by the systems. And the team also found that audio squeezing, which is the act of like taking less instances of the song or squeezing the song, like taking less samples from the song, actually resulted in the ASR systems not picking up the command songs from the music. We'll discuss a little bit more about that. For my personal opinion, the audio turbulence is kind of a bad defense, just because the audio quality would be affected, and folks go through a lot of trouble to get the best audio quality in headphones and speakers. So not sure how real that solution would be, but audio squeezing seems interesting. Now, one of the challenges that the team encountered during the experiment was the effect of background noise on the actual tests. The team decided not to take background noise into consideration, so a lot of these tests were done in empty rooms. And the thought process behind that was that folks will find themselves in vehicles or in their rooms or in their offices playing music. So there does stand a pretty good chance of the attack still working and affecting a great number of folks. But on the same side, typical ASR systems like Google Home and Alexa do have a harder time, just in general, recognizing speech in rooms with a lot of background noise. So we didn't want to integrate those issues from those physical systems into the experiment we were looking at. So they completely have removed background sound as a variable. Now we're really getting to the meat and potato of what the actual experiment looked like. So what the team did was they actually got a song and really decomposed it using that feature extraction portion of speech to text, and essentially kind of mapped out the different assigned values from the deep neural net to each one of these features. Then having that feature matrix for the entire song, they actually compared what the command outputs of that neural net would have been, and then the team ran a regression algorithm to find the precise place within the song where injecting this command would allow them to have the least amount of perturbations to the original song. So I know that was a mouthful, but it's really interesting, right? So essentially the team had an equation that they were looking to minimize, and a piece of code that would parse through all the different features that were extracted from the original song and compare them against the command, and they would try to find that perfect medium where just a slight variation, a slight change in the original song would output the same desired command from the neural net for the speech to text recognition. This would then allow the team to make the least amount of changes possible to the original song, but still have those key sounds that would then trick the ASR into hearing the command. Something that was discovered while all these tests were being ran was that human ears, in order to actually understand a string of words, if you will, those string of words often had to expand several feature recognitions before a human being could understand the voice. But the team found that for a machine to be able to understand the phrase or the word that was being said, a lot less frames were needed. So this allowed the team to compress the actual command that was being injected into the song and only flip as little amount of data in the song in order to morph it into the command, limiting the amount of distortion that we had to do that they had to do to the song, and at the same time making it as unrecognizable to the human as possible. Now that we've discussed how the team actually inputted the commands into the song, minimizing disturbances to the song and so on, let's talk a little bit about the results and how they were measured, how the effectiveness, I guess, was measured. So on one end of the spectrum, the songs were played and the ASR models for the open source system Kaldi that we had already mentioned, all were able to successfully understand this music. We talked about 100% success rate with a raw file input and 96% success rate with doing it over a speaker. Now, the other aspects of the experiment that needed to be measured were with regards to user perception of the alteration to the song, as well as whether they could make out what those alterations actually were. And essentially the team, like was mentioned, used mechanical torque from Amazon in order to conduct a series of surveys. I believe it was close to 300 surveys of users who would actually listen to a 20-second clip. And after listening to the clip, they would be asked a series of questions, basically. Do you recognize the song? Did you notice anything particular about the song? Did you hear, anything that felt like it was out of place? And if you did, what was it that you heard? And the most amazing part of this was that very little people noticed anything at all. And from those that actually did claim to have noticed a small perturbation, they could not identify what the command actually was. So here you can actually see data that the team compiled regarding the different speakers that they've used, as well as the success rate from each one of those speakers. Obviously, depending on the speaker, things vary a little bit, especially when it's not in a fully controlled environment. When you add that variation, you get variations in success. And something else that I'd like to point out here as well is the SNR value. The SNR value is basically a calculation that determines how much the audio actually deviates from the original. So here we want the number to be as low as possible, which would then imply that the song has been modified very little in order to actually have the ASR system register the command itself. Finally, another result that came out of the questionnaires led the team to believe that there was some genres of music that actually made the commands be less perceptive. It turns out that rap, as an example, made the command more noticeable, while soft music made it a little bit less noticeable, even though at no point did any of the folks being surveyed could actually recognize the command. More people found the perturbations in rap to be more obvious than the perturbations in soft music. All in all, 15% of the participants noticed the abnormality, but none of them could actually identify what the abnormality was. The section before the conclusion of this research paper was focused on kind of understanding a little bit more in depth of how the attack actually worked. And the team did this by looking at the different ways that they could actually break down the command input and the song. So the first thing that they did was to implement their injection model, if you will, of the command into just a blank file, so no music at all. And they were able to obviously get the ASR model to actually recognize the command that was being advertised. The only problem with this is that since it was being injected into an empty audio file, it was very obvious and audible to the end user that the command was actually in the file, correct? You could clearly hear it. So it really didn't meet the requirements of the test, but it was kind of just, again, trying to understand, is this something that can be done and can it work in this way? The second test, kind of complementary to the one that I just mentioned, was the fact that they actually looked at the difference between just a plain song and the empty command, like the empty file with the command injected. And then they looked at the delta, the differences between the two, and they claimed these to be the perturbations that were added to the songs, right? And then they tried to see if the perturbations alone would fool the ASR system, but in fact it did not, which led the team to believe that it is the combination of the two, so the actual injection, not the perturbations alone, but this new file that was being created, that actually caused any changes. For me, the most interesting part and what this section of the paper actually went into was their findings around the fact that ASR could understand features in speech with a lot less frames than a human could. So then it becomes almost very easy to hide these commands inside the frames in a way that the human ears simply won't pick up on it, right? Is the difference between like a very, very, very quick, almost unnoticeable hello, and then hello slowly that, takes a couple of, milliseconds to actually get through a word, and our ears can easily identify that. Going into the conclusion, as was proven by the experiment and by the surveys and by the fact that we had such a success, that the team had such a high success rate, having the ASR identify the commands, the team checked off all the boxes that they were trying to accomplish. So it was an effective real-world audible sound in the form of a song that was being played that the ASR system actually just recognized as a command. It was stealthy because though a small percentage of surveyed test users actually claimed to have noticed the perturbation, they were not able to correctly identify what it was or really say anything more than just, something seems to be a little off. And since it was injected into a song, and presumably we could inject it into any song, distribution channels for this via YouTube or via insert your favorite music streaming app here are very plausible. Now, the team does offer two different ways that folks could potentially defend against these type of attacks. The first one is by introducing turbulence. I think I might have mentioned this a little earlier, just introducing bits and pieces of noise that would actually distort any commands hidden within the features of the song. This doesn't sound too good in my opinion because folks are really just trying to get the best noise quality. They're buying the best headphones, the best speakers, and I don't think that they would be willing to take a hit just in the chance that they might be attacked in this way. The second one was interesting, and it just has to do with the fact that humans can't tell the difference or can't pick up noises that are not a certain number of frames in size, as described in the paper. So a computer can deal with much less frames. But what the paper suggests is, reducing the number of sampling or downsampling will also impede the ASR system from picking up these commands as well. So that's yet another way on how to defend against this. Thank you so much for taking the time to bear with me through this last 26 minutes while I gave you the executive summary of this paper. If you'd like to find out more, I do encourage you to read the actual research paper or watch the presentation. The folks here really did a great job. And yep, thank you so much.